Hey everyone. Today we're going to talk about Stoke's theorem. We're going to state the theorem, talk a little bit about the intuition behind it, and then also work a couple of examples computing both sides of Stoke's theorem and just kind of exploring each type of computation that is present in it. So let's go ahead and get started. We're going to let S be a surface. Partial S, this is going to be the boundary of S, is how we read that. The boundary of S is its boundary. So just so we're kind of clear about what we're talking about here, it could look, for example, something kind of like this, kind of a domed shape. And since it's the surface, we're really only talking about the dome itself, nothing on the inside, just the outside there. And that would be S, and then its boundary would be kind of like the base of it. So in this case, it would be probably circular. And it's just a curve. Boundaries of these kinds of guys are just curves. So given this kind of setup, Stoke's theorem tells us that if we want to take the double integral of over S of the curl of a vector field dot ds, then this is equal to the line integral over the boundary of your surface of f dot dr. And kind of intuitively, what we're looking at here is, if we just kind of look at this one right here, this one tells us kind of like how much f is swirling around your surface. So recall that the curl gives rotation. And we're saying that that has to be equal to how much f has with, how much in common it has with the boundary of S. I do have a picture to show you. So I would have drawn it, but this one's kind of tough to draw. The idea here, looking at sort of this left-hand side of the equation kind of corresponds to this image right here, where we have this surface. Maybe it's just kind of like the filled-in part of a figure-8 shape. And you can kind of see these little circles here are actually just like little swirls of our vector field F, just the little rotations that are in it. We can either add up how much of the rotation, these little rotations are occurring in F on our surface, or we can simply look at the curve on the boundary of our surface and say, okay, how much is our vector field F actually bumping into that curve, and just add that up instead of just looking at each of these individual little curls that are inside of here. So visually, that is what's happening here. All right, so now we do kind of have to talk about orientation for each of these, but I'll have to grab a new page so we have enough space for that. So I'll write this down again. Double integral over S of the curl of f dot ds is equal to the integral over the boundary. And it's a line integral. So now both of these, we need to keep track of orientation, what's going here, or the orientation of what's going on here. So orientation. And it's really important that we make sure that the orientation of this one makes sense with the orientation of this one. If it does make sense, then we're going to see that we get the same sign on both sides of these. Now, if you kind of remember back to our previous videos, being off with our orientation really doesn't affect our value that we get, like the numerical value, but it will affect whether it's a positive or a negative number. And we want to make sure that we get positive on this side and positive on this side, or that we get negative on this side and negative on that side, and then we're not mixing and matching. So to do that, we want to make sure that they agree with each other and kind of make physical sense. So and one way to do this, if we don't have any holes in our surface, is to use the right-hand rule. So for example, if we're kind of looking at our kind of like our dome again here for our surface, and we want to make sure that we want to have an outward pointing normal on the surface. Well, what I can do is say, okay, I want my thumb to point upward then is what that means. And so then I need, in order for this to make sense, I need the orientation of my base to curl in the same direction as my fingers. So that means that ultimately we're going to have, at least in this particular instance, our orientation for the boundary there down at the bottom would have to be a counterclockwise orientation. Now, like I said, this really only works in the case that we have something that doesn't have any holes. So we have like just one surface that can be considered to be like almost like a piece of paper that doesn't have any holes punched in it or anything like that. But in the more general case, when maybe you do have holes in your surface, a lot of people really like to imagine walking along the boundary, and then whenever you're walking along the boundary, you want to make sure that you kept your surface to the left-hand side of you. Okay, so what does that mean? Let's draw kind of a sample here. So this is kind of a popular example. We have this kind of double, it's called a double torus, but it just, it's a something that's got two holes in it, okay? And this guy out here, that's your boundary. And then you have these boundaries that are on the holes as well. So if we want to make sure that we have upward orientation, generally speaking, that's how we normally want to do it. The way to make sure that the orientation on the boundary agrees with the upward orientation on the surface itself is, well, imagine yourself going for a walk along this. You want to walk in the direction that is going to keep the surface on your left. So if I am facing this direction, then my left is going to be, well, over here. So that does indeed keep the surface on my left going this way. So that is the direction that I want my boundary to go. So that's kind of the orientation that we're looking for there. Now, the reason that this becomes really important when we're dealing with like holes and stuff like that is that if I move over to, say like this place over here, okay, so now I'm going for a walk on this boundary because that's also part of our boundary. If I head in this direction, it's actually going to be on my, the surface is now on the opposite side of me. The surface is now going to be on the right-hand side. So I want to make sure that I'm heading in the opposite direction because then my surface will be on the left side like so, like the left side of me if I'm facing this direction. So it's really just a matter of putting yourself in the space and kind of imagining, all right, so let's go for a little walk and see what we need to do in order to make sure that we keep our surface on the left. So notice that a lot of times this is going to result in the boundary around your holes having an opposite orientation of the boundary of the overall space. But the example that I'm going to do here today is going to be focused on, we're just going to have some examples that deal with no holes in the surface. So we're really just going to use more of this right-hand rule, but this is a lot of times a really popular method for figuring out your orientation. So Yeah, let's go ahead and jump into some examples where we just test both sides of the equation there. So we will verify both sides of Stoke's theorem by computing both that double integral over the surface of the curl and the single integral around the curve of f dot dr. Okay, where s and f are given below. And then in each case, we will assume that we want an upward pointing normal vector on our surface. Okay, let's go ahead and get started. So in our first example, we have the surface S equal to x, y, z, such that x squared plus y squared plus z squared is equal to 25. And we have that z is greater than or equal to 0. So our vector field is going to be x, z, negative y. And again, we are computing both sides of the double integral s of the curl of f dot ds and the boundary over s f dot dr, like so. Okay, so before I go too far into this, though, let's go ahead and take a look at what our surface actually is and talk a little bit about the orientation on this thing. So here's our picture. So let's use some different colors. Okay. Here's kind of like the domed part right there. And then my boundary would be given by this kind of circle down here at the bottom. Okay. All right. So on the dome, I want my normal to be pointing upward. Something kind of like that, maybe. So then that means that I want my normal vector pointing upward. So then I need my hand to curl in the counterclockwise direction. So I'm going to want counterclockwise orientation for my disk. Okay. Oh, we'll label this. Okay. So I'm going to call this one right here. This will be my left-hand side, and I'm going to call this one right-hand side, just so we can label them throughout. So for computing the left-hand side, which is what we're going to start with, that double integral over s of the curl f dot ds is equal to the double integral of curl of f evaluated r of u v dotted with a normal vector n du dv. Okay, so this is just reaching back to the formula that we have been using for surface integrals all along. This is not multiplying by r of uv. This is just saying we're going to take the components from r of uv and substitute them into this vector. So let's go ahead and start by parameterizing our curve here. We're going to want to use a spherical setup because our spherical coordinate setup because we're dealing with part of a sphere. So we have r of uv equal to 5 sine of v cosine of u, 5 sine of v sine of u, and then 5 cosine of v. And since we want to go all the way around on the xy plane, I know that u has to be between 0 and 2 pi, and v, because we want the upper half of our sphere, v is between 0 and pi over 2. Just like so. Okay, so then I need my normal vector, which is equal to ru cross rv. And if we kind of remember back to our previous videos when we computed this thing for other spheres, it really doesn't wind up being any different. So I'm going to recycle that information, but just swap out the 5 for whatever number was being used earlier. So then you wind up with negative 25 because it's actually 5 squared that goes there. Sine squared v cosine of u, negative 25 sine squared v sine of u, and then negative 25 sine of v cosine of v. So if we look back at our our parameterization of our surface, or rather more specifically the normal that we're looking for our surface, I guess we had pink, like so. And this was our boundary. Okay, so our normal, looking back at that, we want that to point or face upward like so. And if we look at this guy right here, since every single one of these components is negative, and if we were to plug in really any value, we can look specifically at the any values that we would plug in out of the first octant right here. We're going to wind up with a negative or inward facing vector, and that's not what we want. We want it to be facing outward. So we're going to want to make sure that we multiply by -1 to fix the direction of that. Okay, so yeah, that's pretty much it for n. Now I guess we have to figure out what our curl of f actually is. And that's going to be the I hat, j hat, k hat, partial with respect to x, partial with respect to y, partial with respect to z, x, z, negative y. And after you take that, you just wind up with, well, the 0 vector. So now we have everything that we need to be able to evaluate our integral. So our double integral over S of the curl of f ds, which we want to use S curl of f dot n ds is equal to the double integral over I guess 0 to pi over 2, 0 to 2 pi, 0, 0, 0, dotted with our normal vector, which is this thing up here, the negative 25 sine squared v cosine of u, negative 25 sine squared v sine of u, and then the negative 25 sine of v cosine of u. Oh no, du dv. Okay, so since we have this 0 vector right here, we take the 0 vector dotted with this guy, you're just going to get 0 back. So that means that ultimately our answer is really just 0. So yeah, that's the right-hand side of our, or the left-hand side of our Stokes theorem. So let's take a look at the right-hand side of that. The right-hand side was the part where we just had a line integral over the boundary of the surface, f dot dr. That's equal to the integral from a to b of f of r of t dotted with r prime of t dt. So to be able to do this, we want to look at a parameterization r of t for partial with respect to, or partial, boundary of S, not the partial. It's not a derivative or anything like that. It's just the boundary. So again, kind of looking back to our surface, we had said that since we want the outward or upward pointing normal vector on our dome, the right-hand rule tells us that we're going to need a counterclockwise orientation for the boundary there. So what we're going to get out of that is it's just a circle, like so. And we also do happen to know that this circle has a radius equal to 5 because it is kind of like the midpoint there of our sphere. So we want to parameterize a circle with radius equal to 5, a counterclockwise orientation. And we also know that since it's sitting in the xy plane, that z is equal to 0. So then what we're going to look for then is r of t equal to 5 cosine of t, 5 sine of t, and then 0 in our third component there. So, and then also because we want the circle to go all the way around, we do have that t is between 0 and 2 pi. We take our derivative to get r prime, and we have negative 5 sine of t, 5 cosine of t, and 0. And then we also need to find f of r of t, and that's going to be equal to 5 cosine of t, 0, negative 5 sine of t, because I think this had originally been x, z, and then y, or negative y. So, well, now we have all the pieces that we need to be able to take this integral right here. So, integral over the boundary of S, f dot dr. We rewrote that as integral from a to b of f r of t dotted with r prime of t dt. And this is equal to the integral from 0 to 2 pi of 5 cosine of t, 0, negative 5 sine of t, dotted with negative 5 sine of t, 5 cosine of t, 0 dt, which gives me integral from 0 to 2 pi of negative 25 cosine of t sine of t, which using a u sub, where u is equal to sine of t, what we get out of that is going to be negative 25 1/2 sine squared t from 0 to 2 pi, which is really just equal to 0. So that does indeed agree with what we had gotten for the left-hand side of the equation. So we confirmed that Stoke's theorem does indeed work in this case. Good. We have one more example. All right, so this one, our surface is equal to x, y, z, such that z is equal to 36 minus x squared plus y squared, and then z is greater than or equal to 0. And we're also told that our vector field is equal to y cubed, negative x cubed, and then z squared. So just remind ourselves of what we're doing. Our goal is to compute both sides of our Stokes theorem, which says that the double integral over S of the curl of f dot ds is equal to the single line integral of f dot dr. And before we jump too far into this, let's go ahead and take a look at our shape again. Okay, so this guy right here, this is a paraboloid. And actually, I think we've looked at this shape in a previous video. So this is a paraboloid. It's been flipped upside down, and then it got translated up 36 units. So it's going to look something kind of like that, although maybe a little bit more symmetric in reality. And its boundary will be just kind of like this disc that sits down here in the XY plane. So we want it to, again, earlier we had said that we wanted it to have an outward or upward orientation. So we're looking at our normal vector, looking something kind of like that. And because of that right-hand rule pointing upward, we're going to curl our hands around. We want it to have a counterclockwise orientation. So that's going to look something kind of like this. Just like so. Okay. So the first thing that we're going to do is work with our left-hand side. So that's that double integral over the surface of the curl dot ds, which we had said earlier was equal to the double integral of curl cross f evaluated at r of uv dotted with a normal vector du dv. Okay. I guess, yeah. So this time, our best option for the parameterization is cylindrical coordinates. And I suppose maybe this isn't super cylindrical looking exactly, but the way that we know that we want cylindrical coordinates is because we have this z here by itself. We have x squared, y squared, but no z squared, and then z here by itself again. In this parameterization, u squared is going to be equal to x squared plus y squared. So we're just using u instead of r. So we're going to have r of uv equal to u cosine v u sine of v 0, where u is between 0 and 6, and v is between 0 and 2 pi. And again, this is a shape that we've worked with before, and the reason we know that u is between 0 and 6 is because we need this 36 minus u squared to be greater than or equal to 0. Okay, so now we need to compute our normal vector. And that's just equal to 2u squared cosine v, 2u squared sine of v, and then u. And at this point, we're going to go ahead and check our orientation. So we're going to look at this component right here. It'll tell us where we're pointing up or down. So this is always greater than 0 or equal to 0 because of its bounds that are on it. So it always points upwards. So if we kind of look like that, we have a positive z component. Our thing is always going to point upwards, or our vector is always going to point upwards there. So that means that we do indeed have the right orientation. Great. Okay, so now we just have to compute what actually goes inside of our, or the other piece that goes inside of the integral, which is going to be that cross product there. Or that curl Okay, so f was y cubed minus x cubed, and then we have that z squared, which is equal to, I'm getting 0, 0, negative 3 y squared minus 3x squared from that. Okay. So now at this point, what I want to do is take this and swap out for the pieces that are inside of my parameterization. So let's grab a new page to be able to do that. So this will be equal to 0, 0, and then we have negative 3u squared sine of v squared, and then minus 3u squared cosine squared v. And I'm very glad that there is a negative and a 3u squared on both of these, because this means that I can simplify it down quite a bit to just negative 3u squared for that last component. And now we have all of our pieces that we can put together to create our integral. So that double integral that we started with over s of the curl dot ds, which we said was equal to, I guess I need a new line, double integral over s of cross f r of uv. Again, not multiplication. This is just me denoting that it's getting plugged into this vector here, dotted with n du dv is equal to integral from 0 to 2 pi, integral from 0 to 6, and then we have 0, 0, negative 3u squared, and then dotted with our normal vector, which we determined to be 2u squared cosine v, 2u squared sine of v, and then u. And then you have du dv. Yeah, so what you get out of that is really just going to be the double integral from 0 to 2 pi, integral from 0 to 6, and then negative 3u cubed du dv. And then at this point, this integral is really quite straightforward to compute, and what you ultimately wind up with is negative 1944 pi. So, okay, so this is what we get from the left-hand side of Stokes' theorem. So now we just need to get the right-hand side and check to make sure that they do indeed agree with each other. I need more paper. So, okay, right-hand side. That was the integral over the boundary of S, f dot dr equal to integral from a to b, f of r of t dot r prime of t dt. So the first thing we got to do is find that parameterization, r of t. For that boundary of S. So again, going back to our shape. It's really lopsided. Oh well. The boundary of it is this circle down here at the bottom. And this guy has height 36. Okay. So we already said that it has a counterclockwise orientation. And the other thing that we know about this now is going to be that it is, well, it's a circle-ish. Circle with r equal to 6. Okay, so like if you would think about this being flipped over, which I think is probably the better way to visualize it there. If you flipped it over at the height 36, then you would have to have that your radius would be equal to 6 there, because the height there kind of acts like your radius squared in the equation that you're working with for those. So you get r equal to 6, and we know that it has a counterclockwise orientation. And we also know that, once again, it's sitting in the xy plane, so we know that z has to be equal to 0. So the parameterization that we get for this is r of t equal to 6 cosine t, 6 sine of t, 0. And we have 0 less than or equal to t less than or equal to 2 pi. R prime of t equal to negative 6 sine of t, 6 cosine of t. And then our if we take our vector field and plug those pieces in, what we're going to get out of that will be, I'm just going to put 6 cubed because I don't really want to compute that, sine cubed t. Oh, not sine, that should be a cosine, sorry. So cosine cubed t, and then 6 cubed sine cubed t, and then our last component there is 0. So now we're ready to go ahead and set up our integral. So the integral over the boundary f dot dr was equal to integral from a to b of f of r of t dot r prime of t dt, which is equal to integral from 0 to 2 pi of so 6 cubed sine cubed t negative 6 cubed sine cubed t 0 dotted with negative 6 sine of t, 6 cosine. Oh, something's off. I put sine here again. This should be cosine. This one should be cosine as well. Nope, this one was right the first time. This one should be sine because there was a y here originally. Sorry. And this one is actually supposed to be sine, and then this one does actually wind up being sine. Oh my goodness. Okay, right, because f here had been, I'm just gonna actually write it down. I should learn to start doing this a little bit more often. So negative x cubed, and then there was a z squared here in the last component. So, okay, so just to kind of recap, there was a y here originally, so we had to put in sine for that component there, and then there was an x here originally. I got that one backwards too. Cosine cubed t. All right, there we go. So that should fix that up, and then this one should be cosine cubed t, and then sine cubed, sine cosine t 0. All right, there we go. All right, now we're back on track. So we have the integral from 0 to 2 pi, and we're going to get negative 6 to the 4th. Again, I'm not computing that yet. Sine to the 4th t. Minus 6 to the 4th cosine the 4th t dt. And this actually winds up being a fairly straightforward computation. If you kind of factored a little bit using difference of squares, you wind up being able to use your sine squared, cosine squared identity. It's not too terribly bad, so I'm just going to tell you that the answer winds up being negative 1944 pi once again. So it does indeed agree with what we had gotten previously. So one thing that I do want to point out about these kinds of problems is at least, I mean, it's really common for like homework problems to be like this, okay, compute both sides of Stoke's theorem and all that stuff. But in real life, I mean, there's no point in computing both sides of the same equation, right? So like you may have one physical quantity, but not the other. One of them, depending on your setup, might be easier to compute than the other. So typically speaking, you would only compute one side or the other of this, but the purpose of this exercise has been to see that, okay, yeah, they do indeed wind up being the same thing. So yeah, that's pretty much it. I'll see you guys next time when I talk about Green's theorem, which is really just kind of like a special case of Stoke's theorem.